So we've seen how we draw the basic inverse trig graphs. So when it's just inverse sine x, inverse tan x, and so on. But what happens if we vary it up a bit? So how to draw some inverse trig functions. So 5 inverse sine x on 3. I guess the key to this is just working out the domain and range, and then fitting it into the basic shape that we know. So the domain, well, I know the domain for an inverse sine curve normally is in between -1 and 1. But that's when I have inverse sine of x. I've got inverse sine of x on 3. So x on 3 must go in between -1 and 1. Multiply by 3 and I get the domain. So I now know that on my horizontal axes I'm going to mark -3 and 3. Now the range, we do the same thing, but we've got to be careful because remember that 5 needs to be grouped with the y to work out the range. So it'll be y divided by 5, and inverse sine, you may remember, went between -pi and 2 and pi on 2. So we're going to say y on 5 is in between -pi and 2 and pi on 2. Multiply out by 5 and we get -5 pi on 2, 5 pi on 2. Reality is I draw the same curve for all of them. I just change the values at those 4 key points. So then I just usually get my template and go, there's my inverse sine curve. So y equals 5 inverse sine x on 3. I mean, the only problem I'm ever going to have is if they ask me to draw more than one, I guess, on the same axes, but they don't tend to ask that too much. So there's a inverse sine one. This one's a little bit more interesting. Y equals the inverse tan of the square root of 3 minus x squared. So the domain for an inverse tan curve is all real x. You can sub anything in. But in this case, we're subbing into the square root of 3 minus x squared, which has its own problems. If I had just said to you y equals the square root of 3 minus x squared, you would have said, oh, hang on a sec, whatever's under the square root sign has to be positive. So I've still got that restriction. So yes, you can substitute anything into the inverse tan, but I can't substitute anything into square root of 3 minus x squared. That's what's going to control the domain. So if I solve 3 minus x squared is greater than or equal to 0, I'm only going to go between minus root 3 and root 3. Now that means I've got a restriction on the domain. That's going to affect my range. So clearly now I can't get the complete range from minus pi on 2 to pi on 2. Things I'm noticing as I look at this, it's going to be an even function. Because function negative x will be the same as function x, because all we're doing is squaring the x value. Alright, but the other thing with the restricted domains, we usually like to test the endpoint, see what's happening. So if I sub in x equals root 3, I end up with 0. Inverse tan of 0 is 0. Didn't really need to do that because it's an even function, but okay, it confirms that that is 0 as well. Let's sub in x equals 0, we get inverse tan of root 3, which is pi on 3. So what's this thing going to look like? Its range is 0 to pi on 3. I reckon we'll get something like that. Right? Now, once we've done a little bit of calculus and we can locate things like stationary points, we could confirm that yes, that is a stationary point there and things like that, and that it's always increasing and then it goes decreasing. But there's my inverse tan of the square root of 3 minus x squared. Looks a bit like a semicircle, but clearly it's not, because it doesn't have a consistent radius. Maybe it's might be an ellipse shape, I suppose. Okay. Inverse sine of sine x. Well, clearly it's going to look something like y equals x, because inverse sine and sine should cancel each other out and leave x. But the question is, do we have the whole of the line y equals x, or is something else happening here? So I go back to the idea. Well, I know inverse sine, I can substitute in things in between minus 1 and 1. So this time I'm substituting in the sine x, but I can only do it as long as my answer is in between minus 1 and 1. Well, if we think of sine, it's always in between minus 1 and 1. So I can sub anything I like into this and get an answer. So the domain is all real x. So maybe it is the complete line y equals x. But then we've got to consider the range, because remember the range, it's still an inverse sine function. Even though I can substitute anything I like into the function, I can still only get answers out between minus pi on 2 and pi on 2. So what on earth is it going to look like? Okay, well let's draw up the obvious piece. Right? We said we know it's going to look like y equals x. But we also said the range was minus pi on 2 and pi on 2. So some would say that's the graph. But we've decided that the domain is all real x, so it can't just stop. I mean, what's it going to do? We can sub some more values in, but what we'll find with this one is it zigzags. Ends up zigzagging like the line y equals x, but up and down. So this is one where you can play dot to dot, unlike the sine curve. Well, what if it's the other way round? What if we were to draw y equals sine of the inverse sine of x? Once again, the two things will cancel. And is it y equals x? What's going to happen? The domain. Well, this time I'm substituting into the inverse sine function and then saying what's the sine of that. And inverse sine, I can only substitute in numbers in between minus 1 and 1. So in this case, the domain is minus 1 and 1. The range, I've got a restricted domain, so let's see what happens. When x equals 1, I end up with 1. When x equals minus 1, I end up with minus 1. Well, let's try 0 as well. When x equals 0, I get 0. It's kind of confirming we've got the line y equals x here. Whatever I'm subbing in, I'm getting out. So this one, let's draw her up. And domain minus 1 and 1. The range will end up being minus 1 and 1. But this time we do just have a piece of the line y equals x. And we stop there. It doesn't repeat like the other one did. So you really got to check your domain and range on these ones to what's going to happen. 1C, we get to play with these interesting trig or inverse trig graphs.